go to questions in just a second. Those of you in America, you'll be familiar with March Madness. I think we have a Magnetics March Madness coming up. Coincidentally, I don't know why, but suddenly there's a huge interest in doing the magnetics design. We have our workshop, which we've just moved our main office to Camarillo in California, and we do 20 hours of magnetics design hands-on there. In APEC, there's lots of things going on with PSMA and IEEE. So there's the workshop just before APEC. APEC, of course, itself will have lots of magnetics events. And then after, on Thursday, there'll be the industry session at APEC as well. If you want some more information on this, we have a lot on our website, in our design center. We also have a LinkedIn group where you can ask lots of questions. We've got 6,000 active members going there. And the PSMA past technical presentations are very, very good. So I do encourage you to get in touch with them and go look at the past presentations there. Some super presentation material from many people. I'd like to thank you all for attending. I think we're going to open it up now to questions from our moderators.
All right. Well, thank you very much, Ray. The questions are starting to come in again for everyone on the lines. Please put your questions in the chat window, and we will deal with as many of them as we can. So, Ray, I'll start off with some of the ones that have already come in, I've captured. First one is talking about the saturation levels versus the B at which the core losses are measured. So why do we accept a standard SAT level for ferrite as 300 millitesla, but you show core loss examples in your presentation taken at 100 millitesla?
I believe the slide was 21.
Okay. 21, is this the one?
It was probably 15, I think.
15?
Yeah.
Well, we have to, there's two things going on here. When you're running at a B max of 0.3 Tesla, you're probably not going plus minus 0.3 Tesla unless it's for something like an LLC inductor. So you tend to have a DC saturation, but your AC ripple is not going to be that full amount. And then one of the standards that's in the industry is when we look at the excitation level of 100 millitesla, this is actually a plus minus 100 millitesla. So it's being excited actually 0.2 Tesla peak to peak, which would, be more in line with the 0.3 Tesla maximum flux, which is going to be your current limit level. These little subtleties, core loss is always 0 to peak rather than peak to peak is, everybody knows that if you've been in the industry for a long time. It can be a little confusing if you're new to the industry.
Okay, Ray, a couple of comments rather than questions. Would like to see increased BSAT and losses in the 100 to 500 kilohertz area too. Also want to see powdered ferrite cores. Any comments there?
Well, the powdered ferrite core is interesting, and personally I don't know why it can't be done, but apparently it cannot be done. And we asked this question of our LinkedIn group recently, and somebody said, well, it's the way the sintering is done that you cannot have the binders endure the sintering and the pressing process. I do not know. And these days it's very, very hard to talk to somebody who's a material person in the magnetics vendors that can give us good answers to this. We don't see a lot of participation from them. I don't know whether there's not many of them or they're kept in the dark or there doesn't seem to be this crossover from the people doing the materials to what we want. It seems to be a very indirect path. But yeah, lots of us have brought up that question recently. We'd like to buy, the lowest loss ferrite that's pre-gapped, so with a 100 perm, 200 perm, 50 perm, whichever. But I don't know what the obstacle is to that. Be nice to find out.
Okay, there's a lot of questions coming in. I'm going to do my best to keep up. Is there a frequency range for what you showed as Gen 3?
Well, which one is, which slide is that?
That was where you showed the 4 different generations.
It's 26.
Well, I saw another question from Isaac Cohen on the right, which is the definition of high frequency is meaningless without talking about power. And he's absolutely right, and that'll apply to this slide as well. When they were back at 60 hertz doing 10 megawatts, everything we know about high-frequency magnetics today was done back then, because that was high-frequency magnetics. You know, they had the skin problems, they had core loss problems, they had proximity loss problems, and they came up with flat helical windings, they came up with different shapes, they made sure the gap was well away from the windings. All the things we're rediscovering at 10 megahertz, they knew back then at 60 hertz. So there's always this power frequency curve. So when you ask generation 1, generation 2, generation 1, I mean, you shouldn't use these unless you've got pure DC. As soon as you start putting some ripple current through these, you're going to get some problems. So I think almost all the vendors have gone to a Gen 2 shielded type core with the gap moved. And the downside of going from 2 to 3 is, you know, you've got the flat foil windings, which is great for loss point of view. It's not good from capacitance. But the frequency will greatly depend upon how much ripple current you've got. I mean, you can use a generation 1 at a megahertz if you've got pure DC. If it's a second stage filter and there's only DC going through it, that's fine. You can make the magnetic material out of anything you like, and core loss will not be a problem. Winding loss won't be a problem because there's no excitation of the AC. So you can't really answer the question without knowing the exact power level, the converter, and the AC and DC component. But I see a Gen 4 needed for the LLCs, and the next step of squishing Gen 3 further is going to be difficult because it's already pretty tiny. So different structures will probably emerge, I think.
Okay, while we're on that slide, there's a comment just came in. I'm not sure what IHLP is. That I would consider Gen 4 the variations on IHLP developed since the late 90s.
Could be. And I'm sure Gen 4 will be something that we probably saw back in the 1920s for the 60 hertz guy, just shrunk down way beyond that. So hopefully somebody in the rest of this year will tell us what Gen 4 is going to be. I have some ideas myself, but you know, it's going to be very specific for my particular field.
Comment with regards to the available data. The comment here says EPCOS magnetic design tool allows you to export core loss data to Excel, and it's free.
Lovely. Okay. So the core loss data, the bulk core loss data is there?
That's what the comment says.
Okay. Well, I'd like to see that from every single vendor, that we can get the raw data, then we can throw that to a university or a student or somebody to run with that. And wouldn't it be great if we could just type in a core material and the excitation and temperature, and it'll just drop out the core loss, and we can compare everybody's part instead of looking through the data books.
Hey, very general question here. What are the trends of magnetics with the advent of GaN?
Well, I have to pause a little before answering that one. I mean, the promise of GaN was that we're going to switch so fast that everything's going to shrink and practically disappear. The reality of topology development, and not to be too much of a downer on it, is that a lot of the topologies we're doing these days, we don't really care how fast it switches because we're going to zero voltage. So the anti-parallel diode of a FET is conducting before we turn that FET on. So if we switch in 1 picosecond or 1 nanosecond versus 1 microsecond, the user of the part isn't actually going to notice. So, you know, the GaN guys who thought, well, we're going to go 10 times the frequency, everything's going to shrink 10 times, and they're going to pay us 10 times the price for our parts, probably facing a bit more reality. It's like, well, 10 times isn't going to happen. We've come up with other creative solutions, and your parts are going to work for us if they're the same price as the old parts were. So, yes, there are some applications where we're still hard switching, but if you look at for example, the server industry, they're the most advanced efficiency supplies that you can buy, running 98%, including the PFC, which is just amazing. If you'd done that in the 1980s, you would have made a fortune. But how do they do it? Well, they're using FETs. They're using GaN sometimes because they like the low capacitance drive, But they're all zero voltage switching, and they're switching down at 50 kilohertz or 100 kilohertz. So, incredible performance is achieved through different means. And GaN, we're still waiting to see, yes, it's adding that last little 1%, but it's not changing the industry a factor of 10 at this point that I see.
Okay, let's move on. 30 years ago, neodymium magnetics made a big impact on permanent magnets. Is there an equivalent for cores?
I haven't seen it yet. I'd like to see one, but again, it would be really nice to get some participation from some of the people who do the material science in cores. I mean, are we at the limit with these cores? That did the research stop because there was no more to be had? And I really don't know the answer to that one. But it would be nice, yes. Neodymium did incredible things. It would be nice to have that sudden quantum jump in magnetics, and then we could be having all these conversations at 10 times the frequency. But I haven't seen it on its way yet.
Okay, let's see. Don't magnetics vendors attend power electronics magnetics seminars? So I think that's for the PSMA Magnetics Committee, and I think it's a frustration that they have too, and I think you probably share that frustration, Ray.
I'm not so much frustrated as I'm kind of interested in seeing that. When we started teaching hands-on courses, it took about 10 years before any magnetics company showed up to our courses. And there's this big disconnect between the magnetics companies and the people designing power supplies. So I think the reasons are, several-fold why they don't come is because, they haven't had the budget in the past, and that is changing. There is the need to do that. But also, I mean, if you're talking the magnetics companies in terms of the people who make the cores, not the people who are making off-the-shelf magnetics, they certainly come to our courses, but people making the cores themselves, the materials, no, we've never seen one of those because I'm not sure how many research people they have there anymore. It's a very heavy industrial business of pressing ferrites. And we certainly need more interaction with the core manufacturers to move this forward. But I'd like to know from the core manufacturers, is there much more to be had, or is the conclusion from long ago from your notes it's like, guys, we're done? I don't know the answer to that.
There's a request for clarification here. In the presentation, it was mentioned that the discontinuous conduction mode is advantageous because it enables ZVS. Isn't it ZCS since the inductor current goes to zero?
Yeah, there's a lot of notation on what ZVS and ZCS means. Actually, on one of the transitions, it's both. You're turning on with zero current. But the important thing for all the high-frequency switches nowadays, ZVS won the battle of which one should you do, zero current or zero voltage. And what you mean by ZVS is that when the main device turns on, its voltage is already zero. It's that turn-on loss that really gets you. And the turn-off loss is ameliorated by putting a cap across the device. So it's zero current and zero voltage at turn-on, and then it's zero voltage at turn-off because of the cap that can be added.
Okay. Sorry, it is 5 minutes past the hour, so Ray has agreed to continue on, but I know we're going to start losing some people, so I just want to thank everyone for attending, but we're going to keep going for a little while. There's a few more questions here, and if you've got a couple more questions, Ray is happy to answer them.
Excuse me, Connor?
Yep.
Hey, I had a quick one for Ray on slide 12. And basically, these curves look like there's two overlaid curves with this break point at 50 hours. I'm just curious if you could explain that, and is there anything special about 50?
Yeah, that's a good question. I mean, when I was preparing for this presentation, I've been looking at this curve in Ferroxcube for a long time and just accepted it. And then I looked at it and I said, well, wait a minute, what are we doing here where we've suddenly there's a break at 50 amps per meter. And what they've done, of course, is change the axis, the x-axis at that point. It's gone 3 times, I think it's 3 times, yeah, three times denser on the x-axis. They're trying to condense the curve here without going to a logarithmic curve. And I think this gets to the standards issue, that there's no mention that they've done that. I don't know if I've ever seen a linear axis before where the linear axis changes in the middle without somebody telling you, hey, we changed the scale, and that's why you've got the break at 50 amps per meter. But if you plotted these properly, or as the other vendors plot them, then you just have the continuous BH loop there. But the attempt is to get the data onto a reasonable size graph and not to have to extend too far.
I see. Thank you.
But I think this gets us to the thing of, let's have some standards for doing these things. So when somebody looks at this ferrite versus a different ferrite, every little thing like this creates confusion in the industry, especially for new people coming in.
Hey, Ray, there is a few specific questions about materials. So let me ask one of them here that actually picks up on 2 different materials. Can you opine on the role of amorphous and nanocrystalline type materials? Some nanocrystallines are touted for up to 1.35 Tesla, but they may be geared to higher power levels and certainly carry a high cost. What if the cost?
Well, there's always been the equation that if you want to up the Bmax, you're going to up the dissipation. I haven't seen that violated. So if they're running nanocrystalline, they're running at 1.2. Yes, it's probably much better dissipation than a steel would be, but I sincerely doubt that it would get even close to challenging the ferrites. So I'm not seeing those in switching power supplies, maybe instrumentation applications.
And another material one, what about grain boundary engineered ferrites?
Good question. I'm not a material scientist. I've seen little pictures when I visited Mag Inc. a long time ago of the grain boundaries, but that's a specialty that I'm not that familiar with, except for knowing the terms. But let's hope somebody works on these things and they cause the great improvement that we're looking for. I say we are seeing incremental. I mean, we do see a new ferrite now and then, and it might get, 20%, 30% better in terms of loss. Sometimes I did notice during the 90s, ferrites would come out called new ferrites, but they really weren't. They were old ferrites renamed, and they had suddenly found a good application. But again, nothing that I've seen is heading towards any great breakthrough.
Okay, comment here, obviously from a practicing engineer, what else would be dearly needed is tolerances on power losses and BSAT over production time, etc.
Well, yeah, I would agree with that. That's kind of a little, dark secret of the industry that the core losses are strictly nominal. I have never seen a core manufacturer say, okay, we're going to guarantee your core loss is never going to be more than this. So I always feel bad for the guys in the aerospace industry who have to do their worst-case analysis, because when it comes to core loss, there is no worst-case analysis. And as an experienced engineer, you test and you measure temperatures, and then you add what you think is a reasonable boundary on top of that. But it certainly would be nice to see that pinned down a little more. But from what I gather, the manufacturing of ferrites and ceramic materials in general, it's not an easy process. And trying to, get a boundary, an upper boundary on what the core loss really is going to be difficult for them. If we can just get them to give us much more extensive data and all the data, I think that's probably the most we can ask for from them. But one thing I have seen in the past, which you're probably alluding to, is, I bought core materials from TDKs and Ferroxcube, Mag Inc., etc., and then the customer maybe has gone to a second or third tier supplier that claims to have the same material, and then you put it in your circuit and it's running a lot hotter. And there are no controls on this, there's no standards on this. that are in place right now. It's certainly something that's needed in the future.
Okay, even if you have data from the core manufacturer, the data corresponds to only sinusoidal excitation, whereas real applications are non-sinusoidal. In your experience, how different are the results, and are we able to pinpoint it directly to the nature of the excitation? I think I've seen some discussions in your LinkedIn group on that topic.
Yeah, I mean, this was addressed quite a long time ago by Rudy Severins, where he showed that the triangular excitation at 50% was, within 10% of what the sinusoidal excitation was. So triangular versus a 50% triangle versus sinusoidal is not significantly different. It's certainly probably less than the deviation that they get from one batch of material to another. The more interesting part is, well, when you run at short duty cycles, how does that change? I did an article on that recently, and lots of other research have addressed that when you get down to quite narrow duty cycles, then you are going to see it climbing in the loss. But I don't think this is something that we can expect the core manufacturers to deal with. If they give us just the sinusoidal, we've got lots of different ways of using that data to project what the short duty cycle non-sinusoidal is going to be. And I think it's accurate enough, quite honestly. I know there's going to be talk about this at the PSMA meetings in APEC, where they're going to have some measurement setups and so on. But one thing that always concerns me on measurement setups is that when we used to do research on ferrites at Virginia Tech, the only way to get at the true core loss was calorimetry, because the parts are so good. And extracting, the real loss measurement from electrical waveforms is a real challenge to do. And a lot of the core loss papers you'll see, they get some very nice electronic-only processing to get core losses, but I'm not sure they're working with the very, very low-loss ferrites. Not completely up on this. I don't know how the core manufacturers are actually doing their measurement these days. Maybe they have the accuracy they need, but there you go.
Just given that you've mentioned APEC, just to remind people, there is a pre-APEC workshop on magnetics. You can access that through the PSMA website. That's on March 19th on the Saturday. And then there's also an industry session on the Wednesday afternoon, which I think is March 23rd. Ray, your slide may say March 24th. Right. It's the Wednesday afternoon. Mm-hmm. And Ray, I think you're talking at that one also, right?
Right. Yes, indeed. I'll be talking actually 4 times at APEC. I don't know how that happened, but it's happening. I see a couple of other questions here. Maybe I can...
Yeah, go ahead. Not to put you on the spot, but is Ridley Nace better than the improved Steinmetz equation? I see that one.
Well, I think it's better because all we tried to do was look at a curve and curve fit it. And we're not worried about whether it's hysteresis loss or relaxation loss or this loss or that loss. We took the raw data and we did the best possible curve fit we could do to that. And we tried all different types of approaches to getting there, all different types of functions that would make it work, and we came up with one that fit pretty good. So really, there's 2 ways that core loss analysis is going. There's very deep, insightful, trying to find out what all the mechanisms are, and that's nice, and it's good university research to try and understand these things. But when it comes down to it, all we've got is the raw data for measuring these things. It's strictly empirical. And there's many different improved Steinmetz things, but we're talking about curve fitting in the end. So our equations work very well for some materials, and we kind of stopped with generating the library of cores that we modeled because some of the core materials we ran into, there were things that didn't make any sense. The slopes would kind of go back and forth. They would increase a little bit, then they'd decrease, and then they'd increase again, which got us to the point, well, I don't really trust the data from the manufacturer. Is it good data, or did they draw their curves properly? And this is part of why I'm saying, it'd be really nice to get that raw data from everybody and then go back to them and say, hey, look, we got some spurious points here that don't make a lot of sense when we're trying to do our curve fitting. And our formula didn't work for a couple of them because it was so all over the place. And of course, any other improved Steinmetz is going to have the same problem. I mean, it's not going to deal with when it jumps backwards and forwards for no logical reason. But all about Corliss. Now, I see the other question there from Jim Spangler on frequency and duty cycle. The work done by Cliff Jameson. Yeah, I think that was great stuff. That's how to get to short duty cycle, non-sinusoidal dissipation. And he used the apparent frequency method, which I really like. I mean, I've used that one myself. And now there's some talk as well as the relaxation time when the core isn't actually doing anything, it's just being whole constant flux. It can actually dissipate there as well. So, you know, that is not included in there. But until we get good raw data, really good raw data, and then we start applying these methods, we're not going to know which one is best, but almost anything is better than what's coming from the manufacturers right now, I think.
Okay. Ray, you can see the questions too, so if you have a couple of them you want to pick up on, go ahead, or I'll keep asking.
We have some planar PCB magnetics. Somebody asking whether you can apply a planar PCB to multi-kilowatt. It's like, absolutely, yeah, it's been done. Some of the first planars I ever saw were done at IBM for their servers 25 years ago, and they just had a great big E-core with a bus bar running through it. You know, we have to define what planar means carefully. You know, do you mean a PC board with a core over it? Or is a slab of copper running through either side of a window, is that a planar? They all get called planars. But certainly the latter is applied, you know, in the megawatt area. So planar, it's never truly planar. It just means it's a lower profile than a previous design. But planar is certainly not restricted to PC board designs, which can have a lot of problems. They've been around a long, long time, but PC board transformers certainly do not dominate the market. We're still using discrete parts. Wire and cores still works a little better in many cases than the PC board planars. And
okay. There's a comment here about variations with frequency, temperature, and pressure. Even I think we've kind of already addressed the tolerance.
I haven't seen pressure. I've never considered that before. I'm not sure the core materials really change that substantially with pressure because they're such hard materials anyway. But you know, it's an inexact science, and certainly there could be other effects as well. The effect of temperature is important. I'm glad to see finally that the magnetics vendors are going beyond 100 degrees C. It used to be, I think, only Mag Inc. had a good curve from, you know, minus 25 to 100 degrees C and showed the whole set of data. Now I'm seeing that from other vendors as well. Lots of them used to do just 0 degrees and 100 degrees. But high temperature is a changing thing these days. It used to be 100 degrees C and you knew you were in trouble. And I'm visiting companies now and doing a course last year at a company where 200 degrees C was their ambient. So the world has changed a little bit in what hot means anymore.
Okay. As a follow-up there on the planar, what are the performance characteristics that PCB planars can't match? Not sure I follow the question fully. Okay. And then there's a comment, core material losses do go up with pressure, for example, potting. Yeah, I guess some of us have seen that where the potting gets into the...
I think the PCB planar question gets to my comment just now that sometimes, you know, a PCB planar is not the right way to go. And planars are very interesting to see the development because originally people thought, well, if I can put a core around my PC board, then I've got a free magnetic, except for the cost of the core. And that was quite true in the early 1980s. Where labor was expensive and PC boards were relatively cheap. But things have changed now that PC board material is very expensive. So if you're on a motherboard of a microprocessor or computer, and you tell them, well, I need a couple of square inches just to put my core around the board of your valuable 30-layer PC board, they're going to laugh at you. And they'll say, well, you can't have that much space. We're using it for communications or whatever they like to do, so please give us that old toroid and stand it up so that you don't steal too much space. But the performance things that are going on is, if you have a multiple-layer PC board and you want to turn it into inductor, because there's some free space on there, and you say, okay, I've got 20 layers on there, you have to think about, well, how is a 20-layer PC board made? And it's fabricated by making lots of 2-layer PC boards, pressing them all together, and then getting solder to fill in between all the layers. And even though PC board planers seem nice and reliable and a good way to go, is actually a 20-layer PC board with, blind buried vias is not a very reliable way to carry a high current. And wrapping a piece of wire is a lot more reliable in terms of getting the current from A to B. So this is what people have discovered, that, using planar PC boards, you have to be careful because there's reliability issues and cost issues involved there as well.
Okay. Did you see the clarifying comment about pressure? Yes, I've seen that myself when you get potting in a gap or things like that.
Oh, yeah, absolutely. Well, you've got to you've got to be careful with your magnetics about how you gap them. If you do the classic center lab gapping of a transformer and you make that transformer quite small, then mechanical pressure is going to fracture the legs of the core. If you're in a high shock environment area, they're aware of these things coming along, so they'll do a 3-gapped leg for an E-core to make sure that when there is a change in pressure, there isn't a big change in mechanical stress on the part. It's absorbed evenly across the core structure. These are very much mechanical issues. These are, not esoteric magnetics issues. These are, you just look at the thing and you figure out mechanically what's going on and which one is going to be the best way to go.
Hey, where does the aerospace 0.25 Tesla Bmax requirement come from?
Well, from a practical point of view, it's 0.3 is about what you can do, and then they've just put a 20% margin on that and say, okay, this is the absolute. We shall never, ever have a design that exceeds this. So they're just being conservative, but it's a good conservative, certainly for, a mission-critical situation. But, not it's funny when we have aerospace engineers in our courses, not all of them are aware of that anymore. It used to be the old-time designers, everybody knew that 0.25 number. The new designers, there's not always someone there to tell them that is in place. But it's just historical. It's just a conservative approximation to the 0.3. And, of course, 0.3 is the industry conservative to what the saturation really might be.
Okay, and I think just one question we missed along the way, and maybe we'll wrap up then. It's back to the topology question again. When you refer to DCM, don't you mean critical conduction mode on a buck, sources at output voltage and input on drain is higher, not zero on turn on?
Well, there's different ways to look at DCM. If you look at the Vicor application, they let the inductor run negative and didn't just ring the inductor. They stored a little negative current and held it there, ready to re-switch. So you can do the critical conduction mode if you like. You can let it go negative and use the current there as well if you like. There's many, many different flavors of getting that zero voltage. And terminology between critical induction and discontinuous mode, they're very similar, just small differences there. But the Vicor one was interesting in that they let the current go negative and clamped it to that negative current.
Okay, well, I think we'll finish up there. We kept about half the audience 30 minutes later, so appreciate it, and thank you, Ray.
Yeah, and thank you to everybody for attending. It's great to see such interest in magnetics. Magnetics are only going to get more. They're not going to get less as time goes on. But we should all be grateful for that because it's why we all have our jobs. If it was all just silicon and capacitors, then they probably wouldn't need many of us anymore.
Thank you everyone for attending. There is another webinar in a couple of weeks' time. Brian Narveson will discuss developments in 3D packaging with a focus on embedded substrate technologies. More details on the PSMA website, so we hope to see a lot of you again 2 weeks' time. This concludes the call. Thank you everyone.
Thank you. Thank you very much.
Thanks a lot.